QLoRA is a fine-tuning method that combines quantization and LoRa to optimize the fine-tuning process for LLMs. It is designed to reduce the memory requirements and computational power needed for fine-tuning, making it more accessible to researchers with limited resources. QLoRA allows for parameter-efficient fine-tuning of LLMs. It optimizes specific modules within the model rather than the entire model, reducing the number of trainable parameters significantly. By using low-rank matrices to update specific parameters, QLoRA drastically cuts down the number of parameters that need to be trained, reducing the computational resources required for fine-tuning large language models. With quantization, GPU memory usage is much smaller than LoRa, about 75%. QLoRA offers the flexibility to fine-tune for various tasks without requiring significant adjustments to the pre-trained model. This adaptability is facilitated by the ease with which adapters can be exchanged, allowing for swift adaptation to new tasks. This versatility makes QLoRA a valuable tool for addressing diverse and evolving challenges in the field of machine learning and natural language processing. With its capability to seamlessly accommodate different tasks, QLoRA presents an efficient and adaptable solution for a wide array of applications, demonstrating its potential to enhance performance across various domains. QLoRA enables precise modifications by allowing us to specify the layers of the model that receive updates. This level of control over the scope of modification has the potential to mitigate the issue of catastrophic forgetting, where the model forgets previously learned information when new information is learned. Additionally, this targeted approach provides the flexibility to adjust specific aspects of the model without affecting the entire system. This level of granularity in adjustments can lead to more efficient and effective fine-tuning of the model's performance. Fine-tuning large language models has become a popular approach in natural language processing. There are several advanced techniques for fine-tuning LLMs, including LoRa, QLoRA, instruction fine-tuning, and RLHF. Let's explore each of these techniques in more detail. LoRa is a technique that uses low-rank approximation methods to reduce the computational and financial costs of adapting LLMs with billions of parameters to specific tasks or domains. It adds a small number of low-rank adapter layers to a pre-trained LLM, which are then trained on a new dataset to improve the LLM's performance on a specific task. QLoRA is an even more memory-efficient iteration of LoRa. It takes LoRa a step further by quantizing the weights of the pre-trained LLM to 4-bit precision, such as 4-bit instead of 16-bit. This reduces the memory footprint and storage requirements of the fine-tuned LLM. Both LoRa and QLoRA are viable options when it comes to choosing the right solution for your needs. LoRa stands out by providing a superior solution, depending on the specific requirements. Its efficiency and effectiveness make it a favorable choice for various applications. When we want to use either LoRa or QLoRA, we may consider the target efficiency that you need. Although QLoRA further quantizes weights, LoRa offers a better solution depending on the specifications. If GPU memory, longer sequence input, and larger batch size are your targets, QLoRA may be a better option for you. If fine-tuning speed and cost are your considerations, you may consider using LoRa over QLoRA. The impressive memory reduction achieved by QLoRA can be attributed to its utilization of a 4-bit transformer base model instead of the conventional 16-bit. While some may argue that such aggressive quantization can significantly compromise performance, it is important to acknowledge that this is indeed the case. Thus, the primary hurdle lies in finding a way to maintain the exceptional 16-bit performance of LoRa while implementing the 4-bit compression technique utilized by QLoRA. Quantization is the process of compressing the original model by applying quantization to the weight parameters. QLoRA introduces an optimal 4-bit data type called 4-bit normal float, which yields better empirical results than 4-bit integers and 4-bit floats. Double quantization is a technique introduced in QLoRA to further reduce the memory footprint of quantization constants without degrading performance. It works by quantizing the quantization constants. Double quantization is particularly useful for achieving additional memory savings when using small block sizes. CPU paging is used to handle the memory spikes that occur during gradient checkpointing. Gradient checkpointing is a technique used in deep learning to reduce memory usage during backpropagation by storing intermediate activations on the CPU memory instead of the GPU memory. QLoRA employs paged optimizers to gracefully handle the memory spikes that normally occur during gradient checkpointing. Paged optimizers leverage the NVIDIA Unified Memory Subsystem, which automatically copies pages on demand between the CPU and GPU. This allows QLoRA to reduce the GPU memory requirements for fine-tuning a massive language model while maintaining performance. The main idea behind LoRA is to insert a smaller number of new weights into the LLM and only train these new weights, rather than updating all the weights of the model. By doing so, LoRA significantly reduces the number of trainable parameters, making the training process faster and more memory efficient. Traditional data types often face a common problem where outliers significantly deviate from the majority of the data, even if the data follows a Gaussian distribution. This leads to a quantization error on the weight, which is distributed evenly across the x-axis, resulting in inefficient computation and uneven utilization of memory chunks when storing the data. However, this problem can be addressed by normalizing and storing the data, allowing for effective utilization of all bins. Quantile quantization methods achieve this by estimating the quantile of the input tensor using the empirical cumulative distribution function. This method treats very frequent values and values that are not as having the same error. However, quantile estimation can be expensive, limiting its usage. To avoid expensive quantile estimation and approximation errors, it is beneficial when input tensors come from a distribution that is fixed up to a quantization constant that fits exactly into the range of data type. Since most neural network weights have a zero mean and some standard deviation, this method can be easily applied. Double quantization is a method that aims to achieve a further reduction in memory usage by quantizing the quantization constants. In order to achieve precise 4-bit quantization, it is necessary to have a small block size. However, this small block size also leads to a significant increase in memory overhead. By implementing a second round of quantization on the quantization constants, it becomes possible to greatly reduce the memory footprint of these constants. This process involves converting 32-bit constants into 8-bit floats using a block size of 256. As a result, the average memory footprint reduction per parameter amounts to 0.373 bits. Paged optimizers leverage the NVIDIA Unified Memory feature to facilitate seamless and error-free data transfers between the CPU and GPU. This feature operates similarly to regular memory paging between CPU RAM and the disk. By utilizing this feature, QLoRA is able to allocate paged memory for the optimizer states. In the event that the GPU's memory is exhausted, these optimizer states are automatically evicted to the CPU RAM. Subsequently, when the memory is required for the optimizer update step, the paged data is efficiently transferred back into the GPU memory. This ensures smooth GPU processing even when the GPU occasionally experiences out-of-memory situations. Overall, QLoRA is an innovative technique that combines quantization and low-rank adaptation to make fine-tuning large language models more efficient and accessible to researchers with limited resources. It has the potential to democratize the fine-tuning process and enable the development of more powerful language models.